Okay, welcome back to the second talk of the morning session. It's by Yongxiao Li of EPFL. So his title is Bounding Self-Dual L Functions, the Conrey-Iwaniec method revisited. Okay. Okay, so you can just begin whenever you feel convenient.
Okay, thank you so much. Thank you to all the organizers for giving me this opportunity to speak at this very nice meeting. So today I'm going to discuss my joint work with Ramanujan and G. So in post-talk, we already heard of his breakthrough work for any degree D function. So in this talk, I will just focus on one specific case. So here is the plan of today's presentation. So first of all, I would like to recall the subconvexity problem briefly, and then I will discuss fundamental work by Conrey and Iwaniec. Then I will mention Xiaoqing Li's generalization to the GL3 setting. And finally, if time permits, I will discuss a Q aspect analog. So let's recall briefly what is a GL2 Maass class form. So suppose we have the upper half plane, and we know given a matrix there is a linear fractional transformation, and we call F a Maass class form if it is a non-zero function defined on this GL2 space, which is vanished at the infinity and is an eigenfunction of the Laplacian operator. So since F is one periodic, we have this Fourier expansion near the cusp. And furthermore, if we suppose F to be the eigenfunction of all the Hecke operator, then the Fourier coefficient is proportional to the Hecke eigenvalue. And we can pick up this Hecke eigenvalue and generate this Dirichlet series. And we can extend this definition to any GLD setting. So now let's suppose F is a GLD automorphic form, and suppose lambda F is the Hecke eigenvalue. And similarly, we define this air function. A priori, this is defined when the real part is large enough, but we can complete this air function by the factor and infinity. So this completity air function is defined as follows. So we have this parameter, which is called the arithmetic conductor, and we multiply by d many copies of the gamma factor. And with this definition, this completed air function satisfies a functional equation which relates its value at s and 1 minus s via this equation. And this complex number is called a root number. So associated to this air function, if we multiply this arithmetic conductor by the parameter at infinity, we can define a quantity which is called the analytic conductor, measuring the complexity of this air function as sum of the parameter values. For example, in the GL1 setting, if F is either a Dirichlet character or an Archimedean character, then either this moduli Q goes to infinity or this height T goes to infinity, then the analytic conductor is just the product of these two parameters. And if F is a GL2 automorphic form, which is invariant under this action of the Hecke congruent subgroup, then if we multiply this level Q with the parameter at infinity, then they will be the analytic conductor. So from complex analysis, we know If the analytic conductor goes to infinity, then the growth of this air function is dominated by this 1/4 power of this quantity. And if we assume the generalized Lindelof hypothesis, then it can be dominated by any epsilon power of this conductor. So we are interested in finding an exponent lying between the trivial exponent and something that is non-trivial. So if it's the Riemann-Zeta function, then the first result was obtained by Weyl and Hardy-Littlewood, and who obtained an exponent which is better than 1/4. And here, this exponent, we call it the Weyl-type subconvexity. And it has been proved by many authors since then. The best record was kept by Programe. And in case if we consider the Dirichlet air function and let the Q go to infinity, then the first result was obtained by Burgess in the 60s. And rather than 1/4, we have this 3/16. And it was only recently that we have results similar to this Riemann-Zeta function case. And I will discuss this similar result later also. So if F is a automorphic form on G of D, the first case to study usually is consider the case that this F admits certain factorization. For example, if we consider F, which is the product of a fixed cos form times a varying character, then there might be more structure to play with, and then people might be able to obtain some results. Indeed, in the GR2, this is the first case that has been studied by Duke, Friedlander, and Iwaniec. So they consider the case that this little f is a fixed cos form, and let chi be a character of large conductor. And then the arithmetic conductor associated to this product is equal to Q squared, and they were able to obtain a power saving. And this exponent has been improved since then by many people. For example, the saving 1/16, this is consistent with the Dirichlet air function saving, and it has been proved by many people using different methods. If we assume the central air value to be non-negative, then we have something better, which is a saving of 1/12. And this is similar to the, yes, so these two are of the same quality, and it has been proved in the rational case by Conrey-Iwaniec and Pedro Yang, and it was extended to other number fields by Paul Nielsen, Bakanova, Freelango, and Han Wu. Do you have any questions so far? Okay. So now I will start to discuss a work by Conrey and Iwaniec. So let's consider the air function, which is fixed cos form Fj times the Dirichlet character. We consider this air function the cubic moment, and here we are summing over the space and the cos form of level dividing Q of trivial central character, and we complete this summation by its continuous spectrum. Namely, we replace this Fj by Eisenstein series. Then the summation, this discrete sum becomes this integral. And then we can apply some spectral trace formula. Conrey and Iwaniec was able to obtain upper bound from the Weyl law. We know in this summation there are about q many terms, and we divide by 1 over Q. So this upper bound is consistent with the Lindelof hypothesis. And here I just point out here, the conductor of this individual function is Q squared. If we write to cubic power, then the conductor is Q to the 6th. And the family here, we are summing over is of size Q. So the logarithmic ratio of this problem is equal to 6. So this seems to be one of the thresholds that people have been able to obtain a Lindelof on average result. For the Conrey and Iwaniec, they restrict this character chi to be a real character. Then according to the results of Guo, we know each air function is non-negative. Therefore, we can drop all of the summation in the left-hand side except one single one. And in this manner, Conrey and Iwaniec were able to obtain these two upper bounds. Here for the deleted function, they obtain this 1 over 6. And in the twist case, they obtain this 1 over 3. And this exponent here, as we recall, is the first improvement of Borges bound since 60s. And the Conrey-Iwaniec bound were later extended to both the spectral parameter and Q varying aspects by Matthew Yang. And like 2 years ago, it was extended to all characters or modular Q over the rational by Petrol and Yang. And also it was extended to other number field. If we assume the conductor of the character is Q-free, then that was done by Paul. And if we assume the number field is totally real, then that was done by Bakanova, Frelengo, and Wu. So in the pool of Conrey-Iwaniec, there was a hidden identity involved. Namely, they consider the cubic moment of this family. And by using the Kuznetsov trace formula and Poisson summation formula, this cubic moment can be transformed to a dual moment, which is the fourth moment of this the deleted function. So here this C is a deleted character modulo Q, but weighted by an arithmetic weight. This arithmetic weight is defined as follows: is the double sum over the characters, and here H tilde is just some Archimedean weight up to a momentum. This momentum is the central air value at 1. It's not the central value, it's the air function evaluated at 1. So to prove they are bound, Conrey and Iwaniec, after arriving at this stage, they ignore the possible cancellation resulting from the sign change of this character, but rather they put a subnorm over this arithmetic weight. And therefore, we can move out this arithmetic weight and then bound the right-hand side here by the fourth moment of the deleted air function. And as for the fourth moment of air function, deleted air function, we know we have an optimal upper bound. And for this arithmetic character sum, if we apply the Riemann hypothesis by the link, when the modular Q is square free, we can prove that under this normalization, this arithmetic weight is bounded uniformly by 1. And here is bounded by Q to the epsilon. So therefore, they were able to obtain the upper bound Q to the epsilon for this cubic moment. That's roughly a quick sketch of their proof. Do you have any questions? Okay. So as we see, if we would like to improve the upper bounds, then one possibility is to try to detect the sign change for this arithmetic weights and to improve the Q to the epsilon upper bound for this force moment average. But this seems to be difficult because even if this arithmetic weight is identically equal to 1, then it was only like 10 years ago that people are able to obtain a power saving algorithm for this force moment average. And in the case of the Caspidal analogy, then this was obtained like a few years ago by Kowalski, Michel, and Saurabh. They obtained this power saving algorithm for this the products of this air function here, f and g, are two fixed GL2 class form, including the Eisenstein series actually. Now let's discuss an extension to the GL3 setting by Xiaoqing Li. So recall the moments problem considered by Conrey-Iwaniec can also be reinterpreted as follow. So here we have the cubic moment. We can also interpret this average as replacing this cubic moment by a GL3 minimum GL3 Eisenstein series. And here then is a GL3 automorphic form times a GL2 times a character. So Xiaoqing Li, she replaced this Eisenstein series by a Caspidal class form. And she considered the case that the modular Q equal to 1, but the spectral parameter of the Fj varies. She sum over this family. So here T sub j is the spectral parameter. Here if we assume the Laplacian eigenvalue of Fj equal to say lambda j, then lambda j we write as 1/4 plus Tj squared. But here we are summing over a window. The spectral parameter of Fj is between T minus m and T plus m. And according to the Weyl law, the total number of summation in this average is about the size T times m. And she was able to obtain an upper bound T times m up to an epsilon power under this assumption. So this again is a Lindelof on average result. So if we use a result by Lapie, which states that the central error value here is non-negative, then we can drop all of the summation except a single one. And in this way, D was able to obtain the true estimate. So here, capital F is a GS3 class form. In assuming the central error value to be non-negative, we need to assume the form here are self-dual. Here, therefore, they restrict our assumption that this capital F is a self-dual class form. This result states that as the height, the T goes to infinity, we have some non-trivial estimate over the trivial bound. And here the second result states that as the spectral parameter of Fj goes to infinity, we have a similar result. And we can obtain these two estimates simultaneously from this upper bound. So here, these two results were the first subconvexity result on the GL3 setting. And in the past 1 decade, we have already seen many progress, but many of them are along this same direction. The exponent saving 1/8 has been improved since then by quite a few people, including Mickey, Sung, and Ye, and also my collaborator, Ramanujan. So the purpose of our work is to try to revisit this work by Xiaoqing Li, and we are trying to understand the underlying structure and also try to improve this exponent. So that's the main result of our work. So we consider the same family, the first moment, and rather than obtaining the Lindelof on average result under the assumption m greater than this quantity, we do not assume this condition, and we obtain these upper bounds. So the upper bound consists of two factors. The first one is t times m. The second one is this factor. And the first factor will come from the diagonal term contribution after using the Kuznetsov trace formula. This second factor comes from the off-diagonal contribution. And here we do not assume assumption on m. After that, we can try to balance these two terms by setting them to be equal. The optimal choice will be m equal to t1/5. And in this way, we obtain this exponent 6/5, which is a slight improvement over this exponent. Let's recall here, she obtained this 11/8. And later, I will try to explain this exponent is the natural limits that we can obtain by using this method. Maybe I pause for a few seconds to see whether some of you will have some questions. Okay, if that's not the case, so let me make some comments. So here in order to obtain this result, we need to assume this GS3 class form to be self-dual. If we do not assume this condition, there have been some recent work in this direction. The first work was obtained by Munshi. Here he considered the case that the GS3 in the T aspect, and he was able to obtain a power saving which is consistent with this exponent. And before last year, the best exponent is equal to 3/20 by Keshav-Agawa. And like 2 weeks ago, we have seen this new preprint by Agawa, Liang, and Munshi. And in their very important and very complicated work, they were able to improve this exponent to 1/4 by using many techniques, by, for example, calculator sum estimate, large inequality, and so on. And in the GS3 times GS2 in the T aspect setting, the first result was also obtained by Munshi, and he obtained this exponent of saving. Qingfeng Sun and myself, he later gave a slight improvement over this exponent. In the case, if we consider the GS3 times GS2 a function, the spectral parameter of this GS2 goes to infinity, then the first result was obtained by Kumar, obtaining some power saving. And this was later extended to both the spectral parameter and the T go to infinity setting by Binzhong Huang. And he was also able to improve this exponent to the limits of this method. So all of these few words that I mentioned follows the same approach of the method introduced by Munshi, using data third-term method approach. And as we have seen from Paul's talk, for any degree D function, he has obtained this highly non-trivial result. For any degree D, he obtained this power saving. In the case that, that we do not have the conductor dropping phenomenon for the spectral parameter in F. So now let's again mention underlying reciprocity formula within the pool of Xiaoqing Li. The family we are considering is this one, the GS3 times GS2 summing over the GS2 spectral parameter. After using Kuznetsov and Voronoi summation formula, we can transform the first moment average to a dual moment. The dual moment is of the form which is the integration over the GS3 function in the TS space times the Riemann-Zeta function, weighted by some function truncating the supports of this T up to a main term, which is the function of GS3 evaluate 1. And the explicit version of this formula was obtained independently, first in the PhD thesis of Cheng-Han Kwang at Columbia. His approach is using the Poincaré series approach. And we also have seen in Luis Wang's talk this Monday that in his joint work with Peter Humphrey, for the ARP norm, they need to use this kind of reciprocity formula. And their approach in obtaining this formula is via analytic continuation of the Dirichlet series. And the reason we call this kind of formula is Motohashi-type formula is because it was Motohashi who first obtained a formula which is the Riemann-Zeta function force moment can be transformed to a dual moment, which is the cubic moment over the Maass class form function plus the holomorphic class form and plus the Eisenstein series up to a linear term. This formula, if we take this F to be the minimum parabolic Eisenstein series, then this force moment will be equal to this right-hand side. So the formula here can be interpreted as the reverse direction of Motohashi's formula. Maybe I again pause a few seconds.
Oh, your thing, it's finished? Your talk is over?
No, not yet.
That's what I'm saying. It's half an hour only. Okay.
Okay, I'll continue. So now I will discuss, give a quick sketch of our proof. So we use some classical tool, including the approximate functional equation, the Kuznetsov trace formula, Voronoi summation formula, stationary phase analysis, plus Cauchy-Schwarz. So let's recall the approximate functional equation, which states that the central error value of the error function can be approximated by some partial sum, and the length of the partial sum can be truncated at the square of the analytic conductor plus the dual term. This dual term is of similar shape, but taking a complex conjugate. And the Kuznetsov trace formula, if we sum over the GR2 Maass class form, then we have the quasi orthogonality. There is a diagonal term up to off-diagonal term. The off-diagonal term is the sum of Kusterman sum weighted by some integral transform of Bessel function. And we also need to use the G3 Voronoi summation. So the GD Voronoi summation in its most simplified version can be stated as follows. If we have the Hecke eigenvalue weighted by a hypercustomum sum whose index is I, and if we assume this original sum has length of size roughly n, then the Voronoi summation will transform this original sum to a dual sum, which is where the eigenvalue will be weighted by a similar hypercustomum sum, but we change the index to be d minus I. Here d is the degree, and here this fixed constant a will be transformed to its complex to the bar modulo q modulo c, and the dual length can be truncated at the quantitative which is less than c to the d over n. This is an oversimplified version. And the stationary phase method saying that if we have an oscillatory integral, then we can expand this integral at the near the stationary point up to if we suppose this test function to be smooth, then we can, in many cases, we can have an arbitrary power saving algorithm. And the Cauchy-Schwarz inequality states that suppose we have a bilinear sum, and suppose this function phi it depends on n and m. Suppose the n and m cannot be separated from this function, then we can apply the Cauchy-Schwarz inequality. And from the Cauchy-Schwarz, in the case that if we open this square, if m1 does not equal to m2, then we can save something for the case that for the diagonal term. And for the off-diagonal term, because we assume these two functions to be independent, so we always can imagine there are some non-trivial cancellation resulting from the sign change of these two functions. So that's the principle of the last inequality. Now let's go to a quick sketch of our proof. Again, here we are considering the first moment of this air function, which is the GS3 class form times the varying GS2 class form. And our goal is to obtain an upper bound. The upper bound consists of two terms. The first term will be the diagonal term, which is equal to t times m. The off-diagonal term is of this form. So we follow these steps. We first use approximate functional equation, and then we apply the Kuznetsov trace formula, and then we use the GS3 Voronoi summation, and we also use the inverse Manning transform to evaluate some integral transform. Finally, we apply one more functional equation, and we finish by using the last ship inequality. So let's go. So first we use the approximate functional equation to evaluate, to give an approximation of this air function by its partial sum. So the air function, the conductor of this air function is t to the 6. So we can truncate the partial sum at the quantitative square of the conductor, which is t cubed, up to a term coming from here. Now we swap the two summation and we sum over this tj. In doing so, we have the diagonal contribution from the Kuznetsov, which is of this form, plus the off-diagonal term. So that's after we swapping the sum and then evaluating this sum over tj. Now this diagonal term is easy to evaluate because it's the diagonal symbol, and that will give rise to this this factor. As for the off-diagonal term, here we have the summation over this n, and this GS3 Heck eigenvalue is weighted by this Kusterman sum. So the natural move is to apply the Weyl summation to transform this summation to a dual sum. And this will give us the following sum. If we apply the Weyl summation, the original Kusterman sum will be replaced by an identity character, and then times some integral transform of the original weight. So here there is some simplification about our proof. One simplification lies in the use of the new version of the Weyl summation due to Stephen Miller and Feng Zhou. So rather than opening the Kusterman sum here and then apply a version of Weyl summation for GS3 times an identity character, we do not open the Kusterman sum. Rather, we apply this version directly, so that will give us the benefits of reducing many redundant variables. And then now we need to evaluate this integral transform to truncate the new variable. And here, in fact, we do not need to do much work because Matthew Yang already do the analysis for us, because he, in his previous work, he studied this integral transform, which turned out to be approximately equal to some factor times an identity character times this integral. And we can see by applying the Weyl summation, there is an identity character popping up, and in evaluating this integral transform, there is another identity character, and the sign perfectly cancel out. So these two identity character cancel, and there's something similar to the conductor dropping phenomenon. Now we simplify the objects we obtain, and that's the off-diagonal term we obtain at this stage. Here we are using the approximate functional equation. If we would like to relate this partial sum to the original function, this one will be essentially the Riemann-Zeta function, and this second partial sum will be the GS3 function at height t. And that's the dual moment in this problem. Since we are using the partial sum, we can we have the option of reducing the length of this summation by using the functional equation. That's what we did in the case that this n-tilde is long enough. Now we can apply the last inequality to finish the job. Here, this is essentially the second moment of the Riemann-Zeta function, and the upper bound T over M is easy to obtain. The second factor will be the second moment of the GS3 function in the TS space. And here we do not have an optimal result. The optimal result will be replacing this exponent 3/2 by 1. And now we obtain the off-diagonal term can be bounded about by this quantity, and that will be reducing to our final result. So maybe let me make a few comments. So here, as we mentioned, the quality of our subconvexity exponent will relate on the second moment of this integral, the GS3 in the TS space. We do not have a better result rather than 3/2. So if we can improve this exponent, then we can also improve the final result in our power. And suppose we have the best possible for the exponent 1, that we imply the off-diagonal term in the about treatment to be bounded by this quantity, and that will give us the upper bound t to the 1. They will be consistent. They will be consistent with the exponent given by Conrey-Iwaniec and Petrov-Yang. And indeed, if the GL3 class form F is replaced by a GL3 Eisenstein series, that will correspond to a work by Iwaniec, and the best possible error term in this setting was obtained by Zhiqi. We have heard about his talk like 2 days earlier. And here, this exponent might be quite difficult to improve because this function, the conductor in the t aspect is u to the 6, and then here we have u many term here, so it can be quite difficult to improve upon this exponent. But if we consider not the long average but a shorter average, then indeed there have been some improvement in this setting by Agawa, Liang, and Munshi, and we can see the talk of catch up this afternoon. So finally, let me mention another aspect, which is the similar aspect considered by Conrey-Iwaniec. So if we consider not the spectral parameter goes to infinity, but rather the conductor of the character go to infinity, then Boomer obtained these 2 estimates. First of all, for the GL3 class form twisted by a quadratic character of large conductor Q, then he obtained an exponent which is better than the trivial one. And similarly, if we consider the GL3 self-dual class form times the GL2 class form times the Dirichlet character of large conductor, then he also obtained a similar result. And this exponent 5/4, if we compare to previous work by Li, is slightly better. This is because Boomer, he also used a last inequality rather than applying the second Voronoi summation in the proof by Xiaoqing Li. And here, to obtain these 2 results, we also need to use the non-negativity of the air function. And in doing so, we need to assume the character to be a quadratic character and the GL3 class form to be self-dual. If we do not want to assume this such restriction that have been worked out some years ago, in this case by Munshi, and in the second case by Sharma, by using completely different method, namely they are using a delta method approach, and they were able to obtain more general results with slightly less, slightly smaller power saving. So there is a similar Motohashi formula within this problem. If we recall the work by Conrey-Iwaniec, they obtained this result. And Boomer, if we replace this cubic moment by a GL3 Maass class form, then this first moment can be transformed to a dual moment. The dual moment will be the GL3 times a Dirichlet character air function, and then another Dirichlet air function weighted by this arithmetic weight up to a main term. And Boomer obtained this upper bound for this dual moment. This is because he also pulled out the subnorm of this arithmetic weight and then use the Cauchy-Schwarz inequality. And in using Cauchy-Schwarz inequality in studying this second moment of the twisted GL3, he obtained this Q to the 3/2 rather than Q. And they correspond to this factor Q to the 1/4. So to improve this exponent, q to the 1/4, one might think of some possibility. For example, we can try to improve this exponent. That might be quite difficult. Or if we would like to try harder, maybe we do not want to take a Cauchy Schwarz. We would like to improve this upper bound directly. But improving this upper bound directly might be even more difficult, because even if this arithmetic weight is not here, then we do not know how to study this moment. So Boomer, his result was stated for the modular Q to be square free. And this exponent seems to be quite difficult to improve. So therefore, we are trying to consider the case that this Q admits certain factorization. For example, if Q is the product of 2 points. And that's what we are trying currently. So we assume the case that the conductor Q of the character is equal to, say, the product of 2 points. Both of them has some size. Then we can improve this exponent slightly by something better than 5/4. And the best possible exponent that one can obtain seems to be the case that when, for example, the Q2 is of this size and Q1 is of this size, then the best exponent in this case will be consistent in the T-space problem that we mentioned earlier. And in doing this, trying to work this out, we encounter some difficulty due to the family we are summing over. The family we are summing over, the air function does not have constant root number. So now we have started to talk to Peter Humphrey to see whether we can use the analytic continuation approach in the place of the approximate functional equation. So finally, let me mention briefly the idea of our attempt. So our key observation is there is a huge unbalance in the upper bounds by Boomer. Recall he obtained this upper bounds, and there will be always this term here coming from the diagonal term, and he obtained for the off-diagonal term, he obtained this exponent, which is much worse than the one in Conrey-Iwaniec. So our idea is try to sum over a larger family, try to improve this off-diagonal term. So rather than summing over a family of size Q, we are trying to sum over a larger family, but the conductor of the air function remains the same. And in this way, because we have more average, one might hope to improve this off-diagonal term by a tiny, at the cost of increasing this diagonal term by some amount. And then we can try to balance this off-diagonal term and diagonal term to get a best possible exponent. I think this is the technical part of my presentation. So as some of you might heard of, so Chandrasekhar, who was a postdoc at EPF Lausanne, after courageously fighting for units, passed away earlier this year. So already in his PhD thesis, Chandra not only proved advised by Professor Ramanujan at Stanford, he not only proved T-space subconvexity result for GR2 times GR2 Rankin-Selberg air function, which is the first such proof using a circle method approach, but also a combined level aspect for the GR2 times GR2 setting. It is a pity that he left us at a very early age, but for sure he will be remembered by many of us who know him in person. I will stop my presentation here. Thank you all for listening.
Yeah, thank you for a very nice talk. So, any questions? I mean, there should be. There are people working in this area. Yeah. You want this?
Hello,
Yes.
can you hear me?
Yes.
So in your second result in the level aspect, so how do you take advantage of Q1 and Q2? Can you just elaborate it a bit? So why can't you deal with let's say Q2 be prime or?
So here, yeah, here we assume the chi to be modular Q, and Q is equal to Q1 times Q2, and here the advantage come from this Q prime. Here the Q prime is maybe Q1 square times Q2, so it's slightly the larger family. So if we consider the setting of Bloomer, the Q prime will be equal to Q, but here we are choosing some Q prime which is greater than Q. And here here the choice of this Q prime is the place that correspond to our improvement, because after you carry out the diagonal term, if we admit the Q to be Q1 times Q2 in a certain place, there is after using Voronoi summation or evaluate some characters, there will be some similar conductor dropping phenomenon. So that will reduce the size of the conductor in the dual sum. Yeah. Something like that.
Oh, that's nice. You are even in this way you are reducing the size of the conductor a little bit.
Yes. Yes.
Nice. Thank you.
Thank you.
So, any more? Yeah, I just wanted some clarification about your notation. So you are applying that H of Tj, that H tilde is just the Kuznetsov transform, right? Bessel function.
Yes, H tilde is some integral transform depending on this original weight.
Show me the spectral identity page. Will you write the spectral identity?
Yes, let me try to find.
Yeah. So you had some H tilde H somewhere. Yeah. What is this number?
This is something controlling the depending on this little h is some integral transform, which in this case is not very essential because here we are considering the aspect that Q goes to infinity. But if we consider the spectral aspect, then that will be essential here. So it's something controlling the support.
Okay.
Of the summation. Yeah. Or the integral.
Okay, okay. I see. So that is explicitly given any H, you know at least some bound or whatever on H tilde H.
Yeah, I think for example in the work by Peter Humphrey and Liz Van Kind, they in their work there is some also in the work by Kwang by Kwang, they have a very explicit version of this H tilde.
Yeah, so you definitely want it to be non-zero, right? Because as far as I understand, that gives you the main term.
Yes, it's non-zero. Yes, there is something depending on this H, and then which is non-zero. There is some measure in the integral.
Okay, thank you.
Thank you.
Okay, so if there are no more questions, then let's thank the speaker once again. Okay.